Hello everyone, and welcome back to this series on fundamentals of mathematics. In the past couple of videos, we've been focusing on some basics associated to basic set theory, relations, and functions, in particular domain and range and intercepts and symmetry. In this video, we're going to be introducing some of the main and most common elementary functions that you'll probably encounter in the journey of mathematics and also possibly statistics as well. So let's briefly go over a very important definition that we're definitely going to be exploring in a little bit of detail today. So let us assume that F is a relation between two sets S and T, which we've been denoting as subscript S, F, subscript T. F is the name of the relation, S is the domain, T is the codomain, which can also be taken to be the range of that relation. And sometimes we will write this in mapping notation, i.e. F maps the set S to the set T, right? So these two notations are typically synonymous in most circumstances, unless otherwise specified. So let's assume that F is a relation such that for each x in S, there is at most one y that is associated to that particular domain value x, i.e. x is mapped to the element y. So x goes to y, i.e. x is related to y via the relation f. Then, if there is at most one y associated to that particular domain value x, then we call that relation f a function, and some people will even be a little bit more specific, a univariate function, and some people will also say of which variable. In particular, we're talking about the default variable y. And we will write, since f sends the element x to y, we will write f of x is equal to y. So these are two ways of saying the same exact thing. So y is an element, f of x also must be an element. Therefore, when someone says, is f of x a function? The answer is no. The function is f. X is an element in the domain of f, and f of x is what some people also call the image of x under f, and it has another name. Its name is y. So what we're going to do today is we're going to go through some of the basic functions that are often encountered in the realm of mathematics. So the first function, which I'm just going to abbreviate by f sub 1 of x, is going to be equal to c, where c is any real number, and this is known as the constant function. So for example, f of x is equal to 3, f of x is equal to 2, f of x is equal to 10, and we're considering for all values x in the possible domain that we can choose for this particular function. So what does this look like? So if we look at a table of values, for example, xy, for example, minus 3, minus 2, minus 1, 0, 1, and 2, when f of x is, what is f of x equal to, for example, when f of x is equal to 5. So when x is equal to 3, y is equal to 5. When x is equal to 10, y is equal to 5. So regardless of the x value for which I've chosen here, all of the values are going to be 5. So if I let this be my x-axis and this be my y, there's going to be a bunch of values here that are going to be equal to 5. Regardless of the value for which I have chosen, that is going to be my curve or my relation f. Right? So all constant functions, which is a special case of linear functions, are all horizontal lines, right? So horizontal lines are always going to have one y-intercept. It's possible that a horizontal line has infinitely many x-intercepts if it's entirely the x-axis, but generally speaking, all constant functions are not one-to-one. So they're not one-to-one functions, but they are functions nonetheless. Another function that is also a line is going to be the general linear function, which we're just going to be represented by f of x is equal to x. And this is referred to as the identity function. Some people also call it the identity linear function. So why did they give it this name? So again, let's construct a table of values. Minus 2, minus 1, 0, 1, and 2. So when x is equal to minus 2, y would be equal to minus 2. When x is equal to minus 1, y would be equal to minus 1. Wherever the x value is, the y value will be the same exact thing. So if we try to plot these points, you're going to have points that sort of follow this particular relation. So if we extrapolate these points, you're going to get this particular relation, which is the identity linear function, which obviously does not have x-axis symmetry, it doesn't have y-axis symmetry, but it does have origin symmetry. So that's actually pretty nice. So let's actually go over the domain and range for these two basic functions. So let's assume we have f of x is equal to 5. What is the domain and range of this? So the largest possible domain we can choose for this particular relation is, of course, going to be the set of real numbers, but the range for this particular relation is just going to be the number that the constant function is equal to, because that's the only y value that it can attain. And also, if we consider g of x is equal to x, our identity linear function, the domain can be chosen to be equal to the set of all real numbers. And since all of the x values are also the same as the y values, if we choose the domain to be equal to r, the range of that identity function will also be equal to the set of real numbers as well. Before we get into the next family of elementary functions that we're going to discuss, I just want to introduce a couple basic transformations of the identity linear function. So let's assume we're looking at the function f of x is equal to x plus 5. So keep in mind we're going to be adding 5 to all of the outputs of the identity linear function, or you could view this as adding 5 to each of the inputs of the function. Equivalent ways for this function, but not always equivalent for a general function, right? So if we view things from this perspective, then it's actually safer to interpret this as up 5 units. So this is the same as up 5 units. And if we think of, for example, another function, for example, if we consider f of x is equal to x minus 2, this is going to be viewed as down 2 units. So we can go down 2 units when we're subtracting 2 from the outputs, right? So notice I'm focusing on the outputs plus 5, outputs minus 2. So every time we affect the outputs, that's always going to be a vertical transformation, either up or down. Now, if we look at things from the horizontal perspective, i.e. we're going to be manipulating the domain values. For example, we can consider, for example, x minus 5. So we're going to take the domain values and subtract 5 from each of them. And also we could do the same, for example, take all the domain values and add 3 of them, and that will be the new output. Then what we can do is interpret this as what? Is this going to be left 5 or right 5? You should be able to find that this is actually going to be right 5 units, because actually this is technically the same as down 5 as well, but this is the same as right 5 units, and therefore this will be the same as left 3 units, right? Because if we look at this, that's going to be 1, 2, 3, all the way up. But keep in mind for the identity function, that's actually equivalent to up 3 as well. But every time you see the parentheses surrounding the transformation, that's going to be a horizontal shift. And everything that's outside the parentheses is going to be typically associated to a vertical shift. Now let's introduce our next elementary function that we want to play with. So let's sort of summarize what we have here so far. So we have our constant function f of x is equal to c, and then our identity linear function f of x is equal to x. So let's introduce our next star of the show, and this is going to be equal to the floor of x. So the floor of x. Some people also call this the greatest integer function of x. So what this is going to be the greatest integer. So keep in mind integer is like -3, -2, -1, 0, 1, 2, and 3, no decimals, less than or equal to x. So let's just do a couple little calculations. So if we take a number, in particular integer, and round that down to this nearest integer, less than or equal to it, it's going to be that integer itself. If we consider, for example, 6.2 and round that down to the nearest integer, that's going to be equal to 6. You could, for example, have 8.99999, round that down to the nearest integer, less than or equal to it, that's going to be equal to 8. And once we get into the negative integers, you have to sort of be careful a little bit. So the greatest integer less than or equal to -3.2 is going to be equal to -4, not -3. So if I were to sketch the graph of this particular function, the floor of x, what is that actually going to look like? So if we look at 0, that's going to round down to 0, 1 is going to round down to 1, 2 is going to round down to 2, minus 1 is going to be rounding down to minus 1, minus 2 is going to be rounding down to that, and so on. Notice all numbers that are greater than or equal to 0 but less than 1 are going to be rounding down to 0, and similar, that's always all going to round down to 1, that's all going to round down to 2, that's all going to round down to negative 1, and that's all going to round down to negative 2, and so on. So this is the graph of the floor relation. And similarly, I'm not going to define this as another function, but another function, which is abbreviated as this is called the ceiling function. So the ceiling function. And that is going to go to the least integer greater than or equal to x, and the similar interpretation follows for that. So what is the domain and range of the floor of x function? So let's think about this. So technically we can take any real number and round that down to the nearest integer less than or equal to that number. So that's going to be the set of real numbers, but the range is going to be the set of integers, because the greatest integer is going to be an integer moreover, therefore the greatest integer can't be, for example, a decimal. And some people will also call this a step function, but there are actually infinitely many different types of step functions, so this is just one of many different types of step functions, but that's a common name for this function as well. So greatest integer function, floor function, step function, not really a good term, but definitely okay, as long as you know what you're talking about. Another function is related to the greatest integer function, and most people abbreviate it as this, so little curly braces. This is the fractional part of x, and some people will define the fractional part of x to be equal to the actual number minus the greatest integer less than or equal to x. So if we look at a couple of examples here, the fractional part of 3.6 is going to be 0.6, because the integer part less than or equal to 3.6 is 3, and we're still going to be left with 0.6 left over. And if we look at, for example, 10.999, the fractional part of that is going to be 0.999. And if we take, for example, the confusing negative integers, for example, negative 3.8, it's very tempting to say that this is equal to 0.8, but it's actually not. So this is going to be equal to minus 3.8 minus the greatest integer less than or equal to minus 3.8, which is minus 3.8 minus negative 4, right? But that's going to be equal to what? That's going to be equal to minus 3.8 plus 4, which is actually equal to 0.2. So it's almost like the complement of what you would get for the positive version of that. And you can maybe even write a nice little statement to sort of say that. All right, so what would the graph of the fractional part function look like? All right, so let's see if we can generate the graph of the fractional part of x. So obviously the fractional part of integers is just going to be equal to 0. So I'm just going to put the integers there. So that's negative 1, negative 2, negative 3, 1, 2, and 3, and 0. And the fractional part is, of course, going to increase slightly. So for example, the fractional part of 0.1 is going to be 0.1, all the way up to 0.9, that's going to be 0.9. All the way up to, for example, 1, and then it's going to shift back to 0. So we can sort of extrapolate this for all of them, and this is going to be the graph of the fractional part of x. So what is going to be the domain of this function? So the domain of this relation is going to be the set of all real numbers, because all real numbers have a fractional part between, for example, 0 and 1. And the range of this is going to be equal to, so all integers have a fractional part of 0, and that's going to go all the way up to 1, but it's not going to include it, because if it had a fractional part of 1, that means it should be able to be associated to another integer, not exactly the integer that it used to be. Up to this point, we've introduced 4 elementary functions that are commonly seen in mathematics: the constant function, the identity linear function, the floor function, and the fractional part function, all of which are linear functions, or what we call piecewise linear functions, in particular pieces of lines that sort of stagger across its domain, where the floor and the fractional part are what we refer to as some of the piecewise linear functions. Now let's talk about a couple of other functions that are actually not linear function, at least not on their global scale. So the fifth function that we're going to be looking at is f of x is equal to x squared, which you should be able to generate the graph of to be this what we call parabola. So parabola shape, which some people refer to in adjective terms as parabolic. So this is what we refer to as a parabola. So clearly we can take any real number and square it and get a real number back. So the domain of a quadratic function is going to be the set of all real numbers. But when we square real numbers, we always get numbers that are non-negative, i.e. either positive or negative. Therefore, the range of the basic quadratic function is going to be the set of real numbers greater than or equal to 0. And some people will also represent that as r subscript greater than or equal to 0 as well. Now let's look at a couple transformational things for quadratics, just in case you may have forgotten how to do these things from, for example, the linear transformations. So let's assume that we have f of x is equal to x squared minus 5. So we're taking the outputs of our basic elementary function and subtracting 5. So this is going to be a downwards transformation, in particular down 5. So if we look at the graph of that, we're going to go to down to 0, 5, and that's going to be the parabola that this is going to have the graph of. Then, for example, let's consider the graph of g of x is equal to x minus 3 squared. So notice that we're taking the domain values, subtracting 3, and then squaring them. So this is a domain transformation. So this is going to be to the right 3 units. So our origin is going to be shifted over to the right 3 units, and that is going to be our new parabola, where that point is 3, 0. Let's look at a couple other transformations that are common. For example, h of x is equal to minus 3x squared. So we're affecting the domain. So notice all of the domain values, that they used to be positive, now they're going to be negated by a factor of 3, so they're going to be a little bit more sharpened. So this is going to grow a little bit more faster compared to, for example, this graph, which would be, for example, like negative x squared. So it's going to be a little bit more rapid in terms of its y values. So instead of being, for example, let's say negative 4 at x is equal to 2 and negative 2, now it's going to be equal to negative 12 at x is equal to 2 and negative 2. All right, so it's going to be a little bit more deeper, I guess you could say. And let's do just one more just for fun. So j of x is equal to minus, let's do minus x plus 4, the quantity squared minus 6. So this is going to be to the left 4, this is going to be down 6, and that's going to be upside down. So if we were to graph that, it's going to be to the left 4, down 6, so that's where our vertex is going to be, and then it's going to be upside down. So it's going to be something along that line. So that's going to be the graph of our relation J. All right, so there's some basic transformations of your quadratic functions, and it's very important to also notice that no function that is of the form f of x is equal to a x minus h squared plus k, which are these transformations in a nutshell, provided that a is not equal to 0, are one-to-one. So they all fail what we call the horizontal line test. So let's introduce our next function in sequence. It's going to be sort of like x squared, but it's going to be one integer higher, so in particular x cubed. So this is going to look like, if you do a table of values, something that looks like this. So this is one-to-one. I'm not going to do any transformations of this because they're not as easy to sort of sketch, but mainly what we would do is focus on that origin point, sort of like the curvature point. So for example, minus x cubed would just be sort of this S-looking curve that sort of goes downwards. But not all cubic functions will look like this. For example, it's possible that you have a cubic function that sort of has that little curvy tail with a maximum and a minimum instead of just this turning point on the middle. So that would be, for example, a fancy transformation. Where we have, for example, like f of x is equal to something x cubed plus something x squared plus something x plus something. If I were to choose my numbers a, b, c, and d correctly, I could get a graph that looks like that. But later when we talk about polynomials in a little bit more detail, we'll explore cubics in a little bit more detail as well. So let's actually explore the function f of x is equal to x squared in a little bit more detail. So this is the graph of our relation, with x on the horizontal, y on the vertical, if we choose the domain for this relation to be equal to the set of real numbers, which is of course not 1 to 1. But again, we do not have to choose the domain to be the set of relations. We can choose, for example, a subset of that domain. For example, if we choose the domain to be equal to, for example, 0 to infinity, then the graph of that relation would just be the right-hand side of that parabola, which is 1 to 1. Right? So what we can do is, since that is 1 to 1, we can, for example, look at its mirror image about the line y is equal to x, and consider this little gray curve here, right? Which is known as what we call the inverse of x, which would be the mirror image about the line y is equal to x. Right? So what is so special about this new function? And this new function I'm going to label as f7. This is going to be equal to the square root function. So the square root function, right? So what exactly is so special about the square root function? So let's sort of outline that again. So let's draw this curve here. Let's assume that this is x and this is y. And this is the graph of the relation, let's call it g, of x is equal to x squared with domain 0 to infinity, and the range obviously 0 to infinity as well. This curve, the square root function, is going to be this one. So this is the relation f of x is equal to the square root of x, with, again, the domain of f also going to be equal to 0 to infinity, and the range also will be 0 to infinity as well. It just doesn't grow as fast. And this is the line y is equal to x. So what is so special about the squared function? Well, again, it's sort of like the inverse or the mirror image of x squared, the right-hand side of the function. And of course, there's some important things that you definitely should know about this. For example, if we look at this particular curve, when we look at, for example, 1, there's only one value associated to that. If we look at 4, there should be only one value associated to that as well, and that's called 2. So therefore, if somebody asks you, what is the square root of 1? You're going to say 1. What is the square root of 0? You're going to say 0. What is the square root of 4? You're going to say 2. What is the square root of 16? You're going to say equal to 4. I do see some people saying that this is equal to plus or minus 1, plus or minus 2, and plus or minus 4, using some false logic. But this symbol is sometimes also referred to as the principal square root function. And this idea of principal and non-principal square roots are associated to multivariate functions. But right now we're only focused on univariate functions. But once we get into multivariate worlds, we'll talk about principal and non-principal square roots a little bit later. But this notation represents the principal square root, which represents the positive value for which you square in order to get the value underneath the radical sign, which is sometimes called the radicand of the expression. Another expression that is very similar to square roots is the cube root of a number x. So what is the cube root? So the cube root of a number, for example, -1, is going to be a number such that you cube it and you get -1. But do we have to define, for example, principal cube roots? The answer is no, because there's actually only one real number that you cube and you get -1, and that's going to be -1. The cube root of, for example, -8 is going to be -2. The cube root of +8 is going to be equal to +2, and so on. So if we were to graph the cube root function, this would look like this. And of course, this is going to share a close relationship with the cube function. So this would be, for example, x cubed. And you can probably guess what function sort of chops these functions in half. That would again be the identity linear function, y is equal to x. So what is the domain and range of the cube root function? So the domain of the cube root function is going to be, again, all real numbers. You can take the domain cube root of any real number and get a real number back. And also the range of the cube root function will also be the set of real numbers as well. So now let us turn to another type of function that's sort of related to the square root and square functions. Let's call this f9. And this is going to be the absolute value function, which is defined to be to the square root of the square of x. So if you're familiar with this graph and you take the absolute value, that's just representing the distance a number is from 0 on the real number line. So if we were to graph these things, you should get the graph of AV. For example, the absolute value of 0 is 0, the absolute value of 1 is 1, the absolute value of minus 1 is 1, the absolute value of 2 is 2, the absolute value of minus 2 is 2, and so on. Right? So obviously any real number has an absolute value, so you can take the domain to be equal to the set of real numbers, and the range of the absolute value function. So when you take the absolute value, you always get a non-negative number, sort of like the square. So this is going to again be 0 to infinity, or r greater than or equal to 0. But again, keep in mind the square root of 4 is 2, not plus or minus 2, else we get some issues for this. Now notice that the absolute value is almost like a linear function in some degree, right? Because notice that that is actually the linear identity function on the right-hand side, and that would be its opposite, y is equal to minus x. So we can actually say that the absolute value of x is equal to x if x is, for example, greater than or equal to 0, or minus x if x is less than 0. And you could interswap the greater than or equal to or less than or equal to on one of these pieces, and you'll still get the same exact graph. So this is, of course, would be a piecewise linear relationship representation of the absolute value function. Let's just do a couple quick transformational exercises on the absolute value just to review. For example, if somebody asked you, what is the graph of the absolute value of x plus 3 minus 2? So again, notice that plus 3 is affecting the domain, so that's obviously going to be to the left 3 units, and that's affecting the range of the absolute value function, so that's going to be, for example, down 2. So if we were to graph this, we would move to the left 3, down 2, facing up, so that would be the graph of this particular relation, f. And let's just do one more just for fun. Let's do g of x is equal to minus absolute value of x plus 8. So notice that that's our parent function, the absolute value of x. We're going to be flipping it upside down, and then we're going to be shifting it up 8 units. Right? So we're going to be going up 8 units, 1, 2, 3, 4, 5, 6, 7, 8, and then we're going to be flipping that upside down. So that's the graph of the relation g. And then let's introduce one more special function, and this is going to be the last of the 10 that I want to introduce that is sort of special. And this is x to the 2/3. So we have, for example, x to the first, which is x to the second, which is x squared, x to the third, which is x cubed. Then we have x to the 1/2, which is the square root, x to the 1/3, which is the cube root. What about x to the 2/3? So this graph is sort of related to another function because, for example, this is the same thing as x to the 1/3 squared, which is the same as the square of the function cube root of x, right? So if you remember what the cube root of x function looks like, that looks like that. So if we square these negative numbers, that's going to come up top, and if we square these positives, they're going to stay positive also. So the graph of this x to the 2/3 is actually going to look sort of like this, which is sort of look like a bird graph. So I'm just going to call it bird graph, right? So what is the domain of bird graph? So the domain of this function, which we labeled f10, obviously is going to be equal to the set of all real numbers because we can take the cube root of any real number and then square it, so that's no big deal. And what would be the range of this relation? So obviously when we square elements, they're always going to be non-negative, so that's obviously going to be equal to 0 and infinity. And of course, 0 to the 2/3 will be 0, so 0 would be included in that particular relation. Let's mention a couple combinations of these functions that are actually common in analysis problems, in particular calculus. For example, let us assume we define f of x to be equal to the absolute value of x divided by x. What would be the domain and range of this function? So the domain of this function obviously is going to be the set of all real numbers because we can take the absolute value of all of them, but we cannot divide by 0. So it's all real numbers except for 0. So all real numbers except for 0. Or in interval notation, minus infinity to 0, union 0 to infinity. But what would be the range of this? Remember, range of functions is not always obvious from the algebraic representation, so sometimes it's useful to analyze the graph of it or analyze the function itself if possible. So keep in mind, if x is less than 0, the absolute value of that number is equal to the minus of the value inside. Because if we have, for example, the absolute value of negative 5, it's the opposite of minus 5, which is 5, right? So if that's the case, then that means f of x is going to be equal to minus x divided by x, provided that x is less than 0, which is going to be equal to minus 1, provided that x is not equal to 0. And if x is positive, then the absolute value of that positive number is going to be equal to that positive number, right? So that means f of x, if x is greater than 0, it's just going to be equal to x divided by x, which is going to be equal to positive 1. And obviously x cannot be equal to 0. So if we look at the graph of this, so we're equal to a constant function on the left and the right, but it's different constant functions. So it's going to be this value for x less than 0, and this value for x is greater than 0. And keep in mind, there should be no closed circles at x equals 0 because you cannot divide by that number. So obviously the range can be seen from this particular graph. The range is going to be equal to the set -1 and 1. There is another function that is actually very closely related to this function, absolute value of x over x, and I just want to sort of introduce it to you just in case you do encounter it. It's called the Sgn function, or the sine of x function, Sign function, and this is defined to be equal to the absolute value of x over x for x not equal to 0 and 0 for x is equal to 0. And this just tells you whether a number is positive, negative, or 0. And the only difference between this and the function that I mentioned above is it has your horizontal lines on the left and right, but it has a closed circle at 0. And defining that allows us to define, for example, a bit of symmetry about this function if interested. So these functions that I've introduced today and their transformations are, of course, some of the basic transformations and functions that you will encounter in your exploration of mathematics and statistics. But there are several other functions that we'll introduce later, for example, exponentials, logarithms, trigonometric, hyperbolic, and other transcendental functions that we'll introduce as needed. But for now, those are the basics, and I hope you enjoyed this video. See you in the next one.